Hi, I'm Alistair, I'm a games designer, and in this video I'd like to show you some fun projects you can create using infrared. So here I've got an infrared LED, and as you can see it looks almost exactly the same as a normal LED like this one. And in fact it behaves almost exactly the same way as well. The difference is that rather than creating white light like this LED, or red or green light, it's currently emitting infrared light, and that's got a wavelength that's outside the range that the normal human eye can detect. That's why you can't see whether the LED is lit or not at the moment. Now, an LED like this is what you'd find at the end of any of your infrared remote controls. Here you'll see at the end of this controller here, you can see a little tip of an infrared LED just like this one. Now, even though the human eye can't detect infrared wavelength light, here's a little trick you can play at home. The sensors inside a webcam or a mobile phone camera have a broader range of wavelengths they can detect than the human eye. So if you load up your mobile phone camera application like this, and then point your television remote control at it, you should be able to see at the end, when I press a button on the remote control, you can actually see the LED flickering, and it's visualized as a kind of a reddy purple glow normally. Now in your television or other device that you control with an infrared remote, you'll get a component that looks like this. This is an infrared receiver module, and it's able to detect the light given off by an infrared LED and to also translate that flickering into a discrete sequence of on and off values. So I've got one of these receiver modules here wired to an Arduino, and the Arduino is running a sketch that's just going to visualize the raw output that the receiver captures when I point my infrared remote control at it. So if I just turn the serial plotter window on like that, now I'm just going to press the number 1 key on my remote control as if I was changing to channel 1. So what you can see there, that was the entire sequence of flashing that the LED did when I pressed that button. So where the line goes high at the beginning, that was a period of time for which the infrared LED was lit for. It then goes off, and then it flashes on and off quite a few times after that. If I press a different key on the remote, you'll see we get a slightly different pattern. Once again, it starts with a long on signal, so that's kind of like a marker to indicate that there's a signal about to be sent. But after that, the length of time for which the LED stays lit for, and also the gap between each, the duration of the gap, changes as well. So you can think of this a bit like a kind of an infrared Morse code if you want. There's a sequence of dots and dashes, or flashes and periods of time when the LED is not flashing. And devices all around you that have remote controls are communicating via this kind of infrared Morse code type signal. But you're not able to see it at all, but it's happening all around you. So long as there is a line of sight between the LED here and the receiver, because remember it is a type of light, so it's not going to go through walls or anything, but you can encode messages using this pattern of flashes. And that's what we're going to do in some of the projects in the rest of this video. So here's one idea for a puzzle you can do using infrared. Here I've got a family television and I've got the infrared remote control that goes with it. Now I've not modified the television itself at all, but underneath the front bezel here I've placed one of those infrared receiver modules I described a moment ago. That is wired to an Arduino, which is round the back, which in turn is wired to a relay controlling this 12-volt mag lock around the front. Now, as you can see, it's Wimbledon fortnight at the moment, so to theme this puzzle a little bit, I've placed a tennis ball on the catch attached to the mag lock here, so that when the mag lock is released, the tennis ball will fly across the room, or maybe fall on the floor. I'm not quite sure what velocity it will be sent at yet. So here's how the puzzle works. Like I say, I've not modified the television at all, so when players have the remote control, they're able to change channels completely as normally, and as far as they're concerned, there's nothing unusual about this television. But the infrared receiver which I placed under the front there is also collecting the signals sent to the television. It's not like infrared signals are somehow consumed by the first device that receives them. You can have any number of receivers all reacting to the same infrared pattern so long as they're within line of sight of the transmitter. So the Arduino around the back is constantly monitoring the pattern of buttons pressed on the remote and the channels which players go to. And that's got a sequence of TV channels saved in the sketch. And when players go to those channels in order, the Arduino will detect that that has occurred, release the relay, activating the maglock, and the tennis ball flies across the room. So let me show you, first of all, the serial monitor output from the Arduino. So you can say the infrared receiver has been activated and is waiting to listen for a code. Now if I first of all go to channel 4 on the remote, for example, you'll see the television detects the signal, but also my serial monitor there, you'll see first of all the pattern of marks and spaces, so that kind of Morse code type pattern, and the channel which it has been compared against and detected. So the Arduino knows we've gone to channel 4. Now let me change to BBC One again. And you'll see again the Arduino has kept track of the channels which I've changed to. If I now go to channel 6, and you'll see it changes again. Now, the code which I've stored in the Arduino, because escape rooms love 4-digit codes, I've put a 4-digit code and it's 4162. Now you'll see I've already entered the first 3 digits of that code, so what I want you to do is watch when I press the final digit and change to BBC2, at which point this tennis ball will presumably be served across the room for an ace. Let's see what happens. So BBC2. Well, it was a little bit undramatic, but you get the idea. So here's how that's all wired together, and it's a relatively straightforward circuit. So I've got the infrared receiver module at the top here, and I've got that wired to ground, to 5-volt supply here, and then this is the signal line which is going to digital pin 2 on the Arduino. Now here I've got kind of the bare infrared receiver component. You can also get receivers mounted on little breakout modules that look a bit like this. If you use one of these instead, it's still wired exactly the same way. It still has ground, 5 volts and a signal line. The advantage of using these little modules is that they generally come with a little LED on the board as well, just shown here. And if you have that, then when the receiver detects a signal, the LED will actually flash on as well. So you get kind of a visual confirmation of a signal being received. But either way, the wiring is identical anyway. And then on this side of the board here, I've got a 5-volt relay. So that is also connected to 5-volt and ground. And then the signal line for the relay is going into analog pin 0. And then over here, I've got the fails secure maglock, and that is running at 12 volts. So it's got a 12-volt supply here. And that 12-volt supply is connected, the negative terminal is directly connected to the maglock. The positive terminal is going to the common input of the relay, and the normally open side of the relay is going to the other pin of the maglock. So when the Arduino sends a trigger signal on this A0 line here, that's going to make the relay flick across from normally closed to normally open, and that's going to allow current from this 12-volt supply here to activate the maglock. Okay, and here's the Arduino code. So as always, start at the top of the code with any definitions. We've got a debug definition here just to output some additional information to the serial monitor. Then we move on to our external libraries, and we're using one library this time, which you can download from the GitHub link here. And that's just going to make it easier to interface with the infrared receiver. Okay, now in the next section we go on to the constants. So these are the variables that are not going to change throughout the duration of the project. And you can see I've got an awful lot of data here. So all of these variables here, you can see that they're constants. They are arrays of unsigned integers, and there's 67 elements in each array. And what these are is these are the pattern of ons and offs and the duration of each of those ons and offs that correspond to the buttons on my infrared remote control from 0 to 9. So if I scroll along, you can see that these patterns actually go on quite a long way. You can also see there's actually quite a lot in common. The starting section of all of these patterns is identical. It's only when they get a little bit further on that we actually see some changes in the duration. So what this represents is this is in array form the same as that plotter, the graph which I showed you of the line with the highs and the low signals. This is exactly the same information, but just represented as an array of values. And now the other thing you might have noticed, you might not seen me use before, is this progmem statement here. So whenever you're storing a lot of information on a device like an Arduino doesn't have a whole lot of memory available to it. And when you compile and upload code, you might have even noticed at the bottom you get some little messages about your compilation. It will tell you how much of the global program memory has been used and how much of various other memory constraints have been used. So when you've got a lot of constant data like this is also true if you've got lots of text. So if you're designing a menu system and you want to have strings of all the text that's displayed on the menu, what you can do is you can copy it to a different area of memory than the area which has your sketch available. And that's what this progmem statement does here. What it's saying is that this is quite a lot of data which I want to save and be able to access on the device. But it's not going to change, so I don't need to store it in the location where the rest of the sketch is going to be stored. I can kind of move it into a different area of memory. And that's what this progmem statement does here. So it's very useful when you want to have a lot of data that you need use of in your program, which like I've got here. What I then do, so having defined each button separately, I'm then going to create an array containing all of those button elements in it. I'm going to put them in an array because that's going to make it easier to loop over them and find out which button has been pressed. I'm then going to define just a variable here which gives me the length of that array. So obviously my array at the moment is going to be 10 elements long because I've got all the buttons from 0 to 9. But you might have other buttons on your controller as well. You might have the volume up or down or power on and off, things like that. So this is a useful way of defining a variable that's going to keep track of the length of an array without having to hard code it each time. So what I'm going to do is I'm going to take the total size of all of the elements in the array. So that is every one of these values added together. And then I'm going to divide it by the size of the first element in the array, which is just this one. Now, because all of my elements are the same length, so they've all got 67 ons and offs in them, that's going to give me the total number it contains. So this is kind of like a useful little dynamic shortcut to create the length of an array by working out the total size of the array and then dividing by the size of just one of the elements in it is going to give you the number of elements. This is where we define what the solution to the puzzle is going to be. So these are the buttons that the player has to press in order. So we've got 4, 1, 6, 2. And they're going to correspond to the buttons in this array here. So this is where I said it's useful to be able to use an index into this array. So we're going to look up the fourth element, which is going to be button 4, then button 1, then button 6, and then button 2. And again here, because this sequence doesn't have to be 4 elements in it, you could just have them press 2 or 3 buttons or have a very complicated sequence they have to follow. So if you make this a different length sequence, then this line here will update a variable called sequence length to reflect the number of channels which the player has to change to in order. And it's done the same way as we did before. It's going to work out the total size of the array and then divide by the size of one element in the array. And this is the pin which we have got the relay module connected to. So in the wiring diagram earlier I showed you that that goes to the signal pin of the relay, and that's what we're going to use to control the maglock. Then we go on to the global section. So this is some variables which are going to be shared throughout all of the functions in the program. So we declare an irrecv object. So this is from that library which we imported at the top of the code, and it is attached to Arduino pin 2. So we declare that in the constructor, and we'll just call it irrecv. We'll also create an object which is going to store the results. So every time that receiver detects and is able to decode an infrared pattern that it's received, it's going to store the results in a variable here. So we'll get that pattern of ons and offs, which we will compare to each of the patterns in this array up here to work out which button was pressed. And then we also have a little counter variable here, sequence progress. So when the player starts to press buttons on the remote and we compare the patterns to the patterns we've got stored at the top here, this variable here is just going to keep track of how far through the code we've got. So it starts at 0, so that means we're checking initially to see whether they press the button for channel 4. Once that's correct, we then increment this counter and we'll go on to the next element. So then we're listening to see whether they press the button for channel 1. If they don't, we go back to the beginning of the sequence again, so this resets to 0. And when we finally get to the end of the sequence, so when this is equal to 4, in this case, we know we've got to the end, that's when the puzzle's solved. Okay, then we go to setup, so when the program first runs or when it's reset, we'll begin a serial monitor connection. We're going to use that serial monitor not only to debug the puzzle, to check what's happening with it, but also to actually get these values here. So you might be wondering where I actually got these numbers from. Well, that's going to be displayed on the serial monitor output when you press a button on your remote control. So when you first run this code, what you're going to do is effectively train it for the particular pattern that the infrared remote you want to use broadcasts. And that's what we're going to need the serial monitor to do, is to get this output here. We'll just dump a little bit of information. We'll enable the infrared receiver so that it starts listening. And then we'll actually print to the serial monitor the pattern that we're looking for as well. So this is all this is going to do is just print this pattern up here, but it's quite useful to remind yourself what pattern you're listening to sometimes in case you forget. And finally, we'll initialize the relay. So the relay module I've got is an active low relay. So we'll initially set it to be high because we want it to be off by default, and that requires writing a high signal to the relay pin to start with. And then we're ready to play. So I've got a couple of helper functions next. The first one is going to send an infrared pattern received to the serial monitor. So this is what I was describing before. This is how we get these lines of code up the top here, how we know what to write in that section here. So it receives that decode results object. So it receives whenever the infrared receiver has been able to interpret one of those flickering patterns, it passes it to here. And it's basically just going to format out in a pretty way the value received. So it just dumps a little bit at the beginning that says unsigned int, and it's going to be an array which is called received data. It says the number of elements in the array, and it loops over them, printing each one out with a comma between them. So this is slightly fiddly to look at, and you also might notice that in the array loop here, instead of starting int I equals 0, which is how you'd generally loop over every element of an array, we actually start at number 1 instead. The reason for that is because in the decode results, the very first element there is actually the length of time that the signal was off before receiving the first high signal. So this is the first signal we want to sort of record. This is the length of that first LED on signal. But in the decode results array, we actually get the length of time prior to that as well. So it's a little bit like saying, well, this is just the length of time since the last time the button was pressed, which is not a hugely useful piece of information for us. So we ignore that value, and instead we just dump out all of the timings for the flashes after that. So that's why we start at I equals 1 here. So what this does is this prints out to the screen a nice value that we can then copy and paste into our code up here. This function here, so compare code, what this does is this takes again one of this decode results objects, so something that the receiver has received. It takes that as one parameter, and it takes it another parameter of a code to compare it against. So that's going to be one of these codes at the top of the screen. So we'll take a received object, we'll take one of the codes at the top as well, and then we're going to compare them to see whether they're equal within a given tolerance. Because one thing you'll notice is that if you press the same button on the remote a few times, you'll actually get slightly different timings each time you press the button. So you don't want to look for an exact match between those two arrays. You want to allow a little bit of leeway either side in the recording. So what we'll do, we'll loop through each element of the received array, again starting at 1, not at 0. And we will take the value that was in the received array, and we'll take the expected value we had for that position. So if we're looking at the first flash or the second flash or the third flash, whatever it is, we'll look at the actual received value and the expected received value for that position in the pattern, and we'll compare the absolute difference between them. If that's greater than the allowed tolerance, which we supplied up here, then the two codes are not equal, so we return false. But if we manage to loop over all the elements of the array, and they've all been within the tolerance, so this line here hasn't triggered, then we'll get to the end and we'll return true. So this is relatively complicated here if you're not familiar with Arduino. There's quite a lot of different things going on here. We've got some notation here which you might not have used. This is for accessing objects or sort of elements of an object. We've got a pointer in the parameter definition here. And also we've got a new function you might not have used, pgm read word. Now remember I said at the top here that I'm using progmem to store these values. So because they've been stored in a different part of memory, to get them back again to use them in the code, I can't simply refer to button 0 straight away. What I need to do is to read it back into a part of memory that I can access, and that's what this pgm read word does. So that's going to read an element from the code which has been saved in progmem. So that's relatively complex, but what it's doing, like I say, is to compare the pattern received to a stored pattern and see whether it's within tolerance or not. That's what that section of code is doing. Here we've got the method that's called when the puzzle has been solved, so when the sequence of channels have been entered in the correct order and we've got to the end of the sequence, we'll dump a little bit of information to the serial monitor. We will write a low signal to the relay. Remember I said this is an active low relay. So what that's going to do is activate the relay just for 200 milliseconds, sorry. So 0.2 of a second. And then we're going to write it back high again, so restore to the default state. And we'll set the sequence progress to 0. So that's like resetting the puzzle again. So I'm using a fail secure maglock here. So it's locked by default. What we're going to do is just send this pulse just for a very brief amount of time, 1/5 of a second. We're going to send a pulse to that maglock. That's going to eject the catch, and then as soon as it's done that, we'll restore high signal to the relay pin so that power is cut to the maglock again. You don't want to continually power those fail secure maglocks at all, or they'll burn out very quickly. So just a very brief pulse of power, and then we return to the default state and reset the progress of the puzzle. And finally we get to the loop function itself. So all those functions up there were kind of helper functions. Now we get to the main program loop that just runs over and over and over while the prop is active. So we'll call the decode method of the IRReceive object, and that's going to sort of query the infrared receiver and see whether it's been able to decode any data. If it has, it's going to store the results of what it could decode in this variable here, and it will also return true, so we'll know that this if statement is true. If that's happened, and if we've allowed the debug statement right at the top of the code, we'll send the pattern to the serial monitor. So recall that that was the script up here that gave a nice pretty printed output of whatever button was pressed. And then what we'll do is we will go and compare the code that's been received to each of the known patterns defined at the top of the code. So for each button that we know about, we'll go over in a loop. We'll call that compare code function, and we'll compare the results that we've received to each element in the button array, and we'll call it with a tolerance of 200. Now I've set 200 there because for this particular remote control you'll notice there's essentially two different lengths of pulse which I get in the code here. One is a length of around 550 and one of which is about 3 times that at 1650. So within a tolerance of 200, I'm allowing the timing of each of these clicks here to be anywhere from 350 to 750, and I'll still accept that as accurate. And this one will be between 1450 and 1850. But I still don't have any intersection between those two values. There's still a clear division between whether it is a short pulse or a long pulse. Even with a 200 tolerance either side. So there's no risk of a short signal being misinterpreted as a long signal. So we'll call it with a tolerance of 200. If we find a match to that, so if compare code returns true, then we'll say, okay, well we found a matching pattern to the pattern that was input. Was that the correct pattern for the stage of the sequence that we were now expecting? So when sequence progress is 0, we're looking at the 0th element of this array. So we've got that a button has been pressed. We found that the matching pattern was that pattern the pattern that corresponds to button 4. If it was, great, that was the one we were looking for. So let's go on to the next element of the sequence, and next time we'll listen for the next button instead. And when we get all the way to the end of the sequence, so when the progress is equal to the sequence length, that means what we've done is we've actually got all the way here, we've had all of these entered in turn, and now we've got to here. Well, that means that the puzzle has been solved, so we'll call the onSolve method. If it wasn't the correct, so if a button has been pressed and it has been detected what button was pressed, but it wasn't the button we were waiting for, then we enter this section here. Okay, so what we'll say then, well, that was the incorrect input, so we'll reset the puzzle back to the beginning again by setting sequence progress to 0. And finally, we'll just put a break here because once we've found a matching button, there's no need to compare it to all the other buttons that we have stored at the top here. Each pattern is unique, so once we've found a match, there's no need to go on and check the other buttons, basically. And finally, we'll just put a little bit of a delay here because we don't want to accidentally record kind of double presses on a button. So we'll wait for half a second before checking again. And then we'll resume the receiver, so we'll go on to ask the receiver, okay, has it received another value? And that's it. Okay, so you can make a puzzle that requires players to change channels on a television using a remote control. But maybe that's not the most exciting use of infrared because, well, that's something we all do every day anyway. So here's another puzzle idea for you. Here I've got a box of remote control Christmas LED lights. And this box contains about 20 of these little LED candles. So they take a single AA battery in each one. And it also comes with a remote control that looks like this. And you can see at the end that this has got an infrared LED on it, just like we were using before. So the way that these work, if I hold a bunch of candles in this hand here, and I press the on button on the remote control, you can see I can make them turn on and glow. If I press the off button, I make them go off again. Now, there's actually a bunch of other buttons on this remote control as well, but they don't seem to do anything, not with these particular candles anyway. So I've just got two infrared patterns to send. I've got on and I've got off. So let's take a look at what the pattern looks like for those two different commands using an Arduino and an infrared receiver like we did earlier. So if I turn on my serial monitor and press the on button to start with, you'll see that that's the pattern of ons and offs that correspond to the infrared LED flickering for the on. When I press off, you'll see we get a different pattern. Now you'll also see that these patterns are actually slightly shorter and simpler than the pattern which we used for the television remote control. I guess because the command set's much simpler here, we just have to worry about ons and offs. And it's only got 23 different durations in it, so it's quite a short, simple signal. So what I did was to take those codes that you see on the serial monitor output there and upload them to sketches running on two Arduinos on the board behind me. And these Arduinos have also got an infrared LED attached to digital pin 3. So the Arduino on the left here, this is going to be blinking this infrared LED using the off pattern of blinks and delays. And it's just going to be looping that over and over again. The Arduino on the right, well, that's going to be making this infrared LED blink using the on pattern over and over again. So it's a little bit like there's someone here holding down the off button on a remote control, and there's someone over this side holding down the on button and just continuously pressing it down. Now you'll also see down the middle of the board I've created a kind of a primitive barrier here so that it's not possible to see the blinking pattern of both LEDs at the same time. Remember that infrared works by line of sight, so wherever we're positioned here we should be able to see either one signal or the other, but not both. So if I take my candles and I hold them at this side to start with, from this position they should be able to detect the infrared LED on this side, which is acting like a beacon that's kind of broadcasting this message over and over again. Now it's telling them to turn off and they're already off, so nothing's going to happen. But hopefully if I move them to the other side of this barrier, what we should see is that they all turn on. So from this location they can only see the beacon that's broadcasting the on signal. Now if I move them back again, oh, that one took a little bit of time. They turn off again. And on and off. So you can see that we can actually change the behaviour of this candle according to its position in space. And you can actually think of quite a few fun ways that you could use this as a puzzle in an escape room. So rather than just having an Arduino board here, supposing that you had a number of shrines positioned around the room and players had to carry a candle to each shrine. At some of them the candle would light up and at some of them they wouldn't, and then maybe that would indicate a pattern of particular deities or something that were important and those ones that weren't important. Or maybe you could actually have the broadcast unit, so the LED flashing in a portable puzzle prop, and instead of having the receiver in the portable element, you had receivers in different areas of the room. Well, if you had it set up like that, you could actually do a very primitive localization system. You could work out in which part of the room this portable element had been carried into based on which receiver was able to pick up its transmission pattern. So it's actually a pretty fun thing to do. Here's how it's wired together. So I've kept the infrared receiver in the circuit diagram here. This is only required when you are first capturing the codes from the infrared remote control which you want to broadcast. So I've kept that in here just to show that it's wired to ground, 5 volt and pin 2. And then once you have captured the codes and you just want to retransmit them again, you don't actually require that anymore. So we'll get rid of that. And then that leaves this very, very simple circuit left over. So we've got an infrared LED, a resistor, and the Arduino itself. So there's really only two important points which I want to take note of here. So the first one is about the actual pin that we're using. Now, generally speaking, when you want to light up an LED from an Arduino, you can use pretty much any of the GPIO pins on the board. But we are making this infrared LED flash in a particular way. We are supplying those patterns of blinks on and off, but we also need to run that pattern of blinks at the correct tempo. So in infrared terms, that's what we refer to as a carrier frequency. And the carrier frequency used by most domestic infrared devices is 38 kilohertz. So that gives you the kind of the smallest possible unit of time which can be transmitted by each flash of the LED and off again. So every blink is a multiple of that particular carrier frequency. Now, in order to get the LED to run at 38 kilohertz, we have to use a pin which supports a timer function. And on an Arduino Uno, there's actually only a handful that can do that. So there's pin 3, you can also use pin 9, but the Arduino library we're using, the IR remote library, assumes that you're going to use pin 3. And if you're going to make any changes from that, you actually have to modify the library itself. So I'm using pin 3 and I suggest you use pin 3 as well. If for some reason you can't and you want to use pin 9 instead, you can do so, but you'll have to edit a few lines of code in the library. And if you're using something like a Mega, there are a few more pins you can use as well. If you're using an ESP8266, for example, well, that has a chip that actually runs at a different frequency, so you'll have to use a modified version of the library for that. So the code which I'm showing today assumes you are using an Arduino Uno or a Nano specifically. Okay, so that's the first thing about the pin. The second thing is about this resistor here. So an infrared LED is just like any other LED. You have to insert a resistor in series to limit the current that flows through the LED. If you don't, then you're going to blow your LED very quickly. And to calculate the value of that resistor, you need to do this little calculation here. So you need two pieces of information from the LED itself that hopefully will come on a data sheet supplied with it. I mean, I've given some typical values here, but these do change, and it is possible to get higher intensity infrared LEDs, which you might want to use to transmit a signal further, for example. But as a result, you might need to adjust this resistor value if you do. But the values which I've supplied here, so we have what's called the forward voltage across the LED, and we also have the typical operating current of the LED. And I've given you, like I say, some typical values here. Forward voltage is often around 1.2, and a typical operating current might be 20 milliamps. To work out the resistor value, what we then do is we take the supply voltage. Now, because we're using an Arduino Uno, when we write a high signal to this pin here, that's going to be 5 volts. So we'll do the supply voltage of 5 volts minus the forward voltage of the LED, so that's 1.2, and that gives us a value of 3.8. We'll then divide by the operating current of the LED, which is 20 milliamps, or when expressed in amps, that's 0.02. So this is our final calculation, 5 minus 1.2 divided by 0.02, and that gives a resistor value of 160 ohms. Now that's a minimum resistor value. you can increase that slightly. It will have the effect of dimming the LED. Not that you're able to perceive that, because obviously it's infrared LED anyway, but it will it won't do any harm to choose a higher resistor value than that. So I think in this circuit here I've actually shown a 220 ohm resistor there, which is what I happen to be using in this particular project, but a value of around that amount you should insert to protect your LED. Like I said, if you want to extend the distance through which this transmitter is going to work, well, to do that you need to make the LED flash brighter, and you might want to look at getting a higher intensity LED to do so. And there are plenty available. If you do that, know that you will probably have to recalculate the resistor value though to go with it. So here's the code that's running on the Arduinos, which are transmitting the infrared messages that are controlling the LEDs. And it's got quite a lot in common with the earlier code I showed for the TV channel changer puzzle. But there's a couple of new bits, and obviously the transmitting section is new. So we're including exactly the same library as we did before. And again, at the top of the code, we're declaring our constant arrays of the patterns corresponding to each signal we want to have. So we've got an on signal and an off signal. And these numbers here were obtained by pointing the infrared remote control at the receiver attached to the Arduino, and then looking at the serial monitor output, which I then copied and pasted back into here. Now, I recommend you probably do that a couple of times for each button and sort of take an average, because you'll find that you might get slightly different valuings each time. So sort of do it a few times, work out the average, copy and paste them back in here. Now, most of the time you'll find that that works absolutely fine. However, if you have difficulties with this code not being kind of understood by the device that you're trying to control, I'll just explain one other fact that might explain and solve that problem as well. So most infrared receivers that I've encountered have a little bit of kind of distortion in the signal that they actually detect. And in all the ones I've seen, that distortion happens in the same way, which is that they tend to overstate the duration by which the LED is lit for, and they tend to understate the duration for which it is off for slightly. So in this pattern here, remember that this first value here, what this number means, this is the length of time that the LED first was lit for. So it was lit for this length of time, then it was off for this length of time, then it was lit again, then it was off, then it was on again, etc, etc. Now, in the TV channel changer puzzle, we were comparing a pattern that we read from the receiver and had trained the code to that pattern. We were comparing that to another signal read by the same receiver. So if there was any kind of bias in the numbers we obtained, it didn't really matter, because the bias was present in the value we were comparing to as well as the value we received. But in this puzzle, we're recording the value using the infrared receiver, but then we're retransmitting it to a different device. So we need to do something to account for that potential bias or distortion in the values. And the way to do that, if you need to, is for each of those odd values that represent a duration for which the LED is lit, you need to reduce them slightly. So if you take an average of values and the average lies in a range, then you want to choose an element that's towards the bottom of the range of values. Or alternatively, you can work out the mean average and then subtract about a value between 20 and 50 from it normally. For the even elements of the array, well, they represent durations when the LED was off, and the receiver tends to understate them slightly. So what we need to do is increase them. So for these elements, what you need to do is work out the average and take one of the values towards the top end of the range of values, or alternatively add on a number somewhere between 20 and 50 again. Now you may not need to do that. Your code might work absolutely fine using the first value you capture. Most infrared devices have a degree of tolerance built into them anyway, so you don't need to get the durations exactly spot on. But I thought I'd mention that just in case you do have problems with this code being detected. That's an adjustment that you might want to try making to see if that fixes it. Okay, so then we get onto the global section. As before, we've got the receiver plugged into pin 2, and we also declare this IR send object. And as I mentioned in the wiring diagram, we don't need to declare a pin that's plugged into in the constructor. It's assumed that that's plugged into pin 3, because that's what the IR remote library we're using assumes in the code. So we don't specify that anywhere, but that's connected to pin 3. In setup, we begin the serial connection. We'll use that to get the output from any codes we want to train on the system, and we'll enable the receiver exactly as before. This function here, this is exactly the same function as we used in the earlier code, and what it's going to do is it's going to take any pattern received from the receiver, and it's going to kind of format it in a nice way and output it to the serial monitor, so that we can copy and paste it, and it will be exactly in the right format to insert at the top of the code listing here. So that's what that function does. And then we get into the main program loops. This is what goes on over and over. This whole section here, this is all just about receiving new codes that you want to train the system to recognize. So this is, as we did before, we'll declare a results object. We'll ask the infrared receiver if it's received a message, and if it's able to decode that message, it will store it in that results object there. We'll then send that result to the serial monitor, and then we'll go on to the next value. So this whole section here is only used when you are training new patterns that you want the system to recognize. Once you've got those values up at the top here, of however many signals you want to recognize, you can ignore or delete or comment out this code completely. You don't need it anymore. You're only using this for training the system. This is the line that actually does all the work in terms of transmitting an infrared pattern. So we've got a send raw signal, and it takes 3 parameters. The first one is, okay, well, what pattern do you want to send? So in this code here, we're sending the on signal, which was this array up here. We also need to tell it how long that pattern is. Now, as it happens here, both of the patterns that we've received have got 23 elements in them. So we could hard code the number 23 here. But if I did that, then that obviously wouldn't work if your particular remote controller had a different number of elements in it instead. So what I've done is a little trick which is kind of useful to know. Whenever you've got an array in C, in Arduino code, and you want to know how many elements there are in that array, you can use a little function like this. So what this does is this takes the total size of the entire array, and it divides it by the size of just one element in that array. So in this case, it's the first element of the array. And assuming that all the elements are the same length, which generally speaking they should be in an array, that will give you the number of elements contained in the array. Okay, this final parameter here, this is the frequency at which we're going to broadcast this infrared pattern. So again, I mentioned this before. If you think of this pattern here representing a rhythm, and it's like a drum being beaten or a Morse code, and we've got shorter and longer notes in that rhythm, then this number here represents the tempo at which that rhythm is being beat out, kind of thing. So it's a value. This is in kilohertz, so it's 38 kilohertz, and that is the carrier frequency at which we're going to broadcast this infrared message. Now, 38 kilohertz is a very standard frequency used by infrared devices. Particularly, it is the frequency which the infrared receiver we're using is going to expect signals to be encoded in. So we're using 38 there, which is a very standard number. You might find devices that operate on a different carrier frequency. If you do, you'll have to have an infrared receiver that is able to demodulate the appropriate frequency as well. Now, on this device, obviously, we have both a receiver and a transmitter of infrared at the moment, and that potentially could present a bit of a conflict because you don't want to accidentally end up receiving the same infrared code that you've just transmitted yourself. So the library we're using actually prevents that. When you start to transmit a message using the send command here, it actually disables the receiver while that happens. Now, so once we've sent our message here, we're going to manually enable the receiver again so that on the next iteration through the loop, we're able to listen to see if any new codes have been learned. And finally, we'll just delay by, so that's 200 milliseconds, and then we'll repeat the whole thing. So this is happening 5 times a second. We're listening to see if there's any new codes to be learned, and we are also broadcasting, in this case, the on signal. And on my other Arduino, I've got exactly the same code. It's just that instead of broadcasting the on signal, it's broadcasting the off signal. So that's literally the only change I've made in the other code. So hopefully those 2 examples have given you some different ideas of the way in which you can use infrared in an escape room puzzle. In the first example with the television, we were listening for a transmitted code from an existing device. In this case, I was just using my television remote. But you could also dress this up in any other sort of puzzle you want. You could put it inside some sort of weapon and turning into an infrared shooting gallery or something like that. In the second example with the candles, well, I was making use of an existing infrared prop, these candles here, and instead I was replicating the functionality of a transmitting device and sort of creating beacons around the room so that these would react differently depending on which beacon they had line of sight to. And there's lots of different kind of mix and match variations you can do along those themes. You can have multiple transmitters which could either be sending the same or different infrared patterns. And you can also have multiple receivers that can either react in the same way or differently based on those patterns. So you can, I really like this idea of like an entire ecosystem of devices kind of broadcasting this hidden network of messages that's going on all around you all the time. And I think there's some really fun puzzles you can do with that. So if you've got any questions or comments, please do write them below and I'll do my best to look at them and get back to you. If you'd like to download the code examples or the wiring diagrams I used, as always, I will upload them to my Patreon account and I'll put a link to that in the description there. So if you head over to Patreon, you can find the accompanying resources, not just for this project, but for all of the projects which I've put on my channel here. And if you're able to support me to make more videos like this in the future, that would be amazing as well. Other than that, I'd just like to say thank you all very much for watching, and I will look forward to seeing you next time. Cheers, bye.